The next topic is the Ramsey-Cass-Koopmans model, and we again split it into two videos. The first part deals with the derivation of the central equations of the model, and the second part deals with an analysis of the model. The Ramsey-Cass-Koopmans model is one of the backbones of modern dynamic macroeconomics, and it lies at the core of most DSGE models and of most economic growth models, and basically it endogenizes the saving rate in the Solow framework. If you need a repetition of dynamic optimization, then I recommend to go to the playlist on the crash course on dynamic optimization for economists, because basically this model relies on dynamic optimization. It was introduced by Frank Ramsey in the 1920s, and he solved the dynamic optimization problem of households to consume an optimal amount over their infinite life cycle, basically. Back then, at that point, it was rather complicated and difficult to grasp by many people, so it was kind of rediscovered in the 1960s by Cass and Koopmans, and only then became popular in economics. You can find good textbook treatments on this, for example, Chapter 2 of Barrow and Saleh-Martin, the book on economic growth in 2004, or Chapter 8 in Asimoglu, Introduction to Modern Economic Growth, Chapter 13 in the book by Ben Hydra, Foundations of Modern Macroeconomics, or you can also find it in Chapter 5 of the book that I've written with David Bloom on automation and its macroeconomic consequences, theory, evidence, and social impacts.
Now, as we just said, the Ramsey-Cass-Koopmans framework goes back to Frank Ramsey, who solved the individual optimization problem. And a general equilibrium structure was introduced by Cass and Koopmans in the 1960s. And basically, the Ramsey-Cass-Koopmans framework is a Solow model, but with an endogenous savings decision. So you know from the Solow model, we have one dynamic equation, the fundamental equation, that determines the evolution of the economy. And in this fundamental equation, we have that the evolution of the capital stock depends on the exogenous saving rate that households have. So how much they save as an exogenously given fraction of total income in the economy. Now, however, the consumption savings choice is endogenous, and that means that we need a second equation. So we have one equation for the capital stock, but we have a second equation that determines the evolution of consumption, and the level of consumption shows up in the dynamic equation for the capital stock. So as before, in the chapter on dynamic optimization, we have two differential equations in two unknowns, and they together determine the evolution of the economy over time. The difference to the previous section, to dynamic optimization, is that we have a general equilibrium structure implying that the wage rate and the interest rate will not be exogenously given anymore. Instead, they are now determined by the interactions of households and firms on the market, and in equilibrium they will adjust such that the demand for capital by the firms is the same as the supply of the households in terms of capital by what they save, and labor supply by households is the same as labor demand by firms. In the basic model, we assume that labor supply is exogenous, which makes things quite a lot easier. Again, households maximize the discounted stream of lifetime utility as it is generated by consumption, and firms maximize their profits by choosing optimal factor inputs. Households are identical, they do not have market power, and they, as I said before, inelastically supply 1 unit of labor on the labor market and earn the wage W for that. To justify the infinite time horizon, it's assumed that households care for their children with perfect altruism, so we can write down the optimization problem in infinite time, and we normalize the number of households, if you will, to 1 at time 0, but we allow for population growth, which is then a growth in the size of the household, basically, over time. Now, in such a setting, we can proceed as if there was a representative household, meaning that the choice of this representative household stands for all the households in the economy. Now, we assume that the population grows at rate n, so that's the population growth rate. And that implies that we do not only have a discount factor to take care of, but we also have a growth factor in the utility function. So the household maximizes future utility. Instantaneous utility is u of c again, from time 0 to time infinity, but under the condition that the household itself grows at rate n. And a so-called Benthamite utility function takes this into account, that this increases overall utility of the household, because the Benthamite utility concept cares for the aggregate level of utility, and in this case aggregate utility refers to household utility. However, again, as before, individuals discount the future at the rate rho, so we also have the discount factor applied in the lifetime utility function. And now one crucial condition has to be fulfilled, and that is that the discount factor, which weighs down future utility, is in absolute terms higher than the population growth rate n. Otherwise, the integral here would not be bounded. It would basically go to infinity, and only if the time preference rate is higher than the rate of population growth does this integral converge. So we have a finite value of this integral, and that's necessary for a solution. Typically, this assumption is not a problem at all. It tends to be fulfilled. Population growth rates all over the world tend to be rather low, and the time preference of households is often assumed to be around 5%, and 5% is a rate that no population typically uses to grow over time. Now again, as before, we have that a consumer has wealth A, lowercase a, that's per capita wealth, and the consumer gets asset income, the interest rate, times wealth A at each instant, and she earns a labor income W on the normalized labor input. Then assets evolve according to the equation as we have it here, that the time derivative of assets increases with income, so that's wage income plus asset income, and it decreases with consumption. That's the same as before, but now we have an additional term at the end of this expression, and this term takes into account population growth. So if assets are defined in per capita terms, that means that faster population growth leads to a dilution of per capita assets. So ceteris paribus, if the population grows faster, or in this case the household grows faster, then assets per person would grow at a lower rate. And you can derive this equation by the definition of per capita assets as aggregate assets divided by the population size, or the household size in this case. That's analogous to capital dilution in the Solow model. So in the Solow model, if you reformulate the model in terms of per capita variables instead of in aggregate variables, then also such a term shows up in the fundamental equation for the evolution of capital per capita. Now the following steps are as in the previous chapter, as in case of the example that we had in dynamic optimization, except that the population growth rate is now taken into account. So previously we had that the population stayed constant, and then after we've solved for the optimization problem, we will see that we also need to take the general equilibrium structure of the model into account, because at equilibrium, as I said before, the interest rate and the wage rate that were given as exogenous in the example in dynamic optimization, they are now determined as endogenous variables. So once we have the dynamic equations for optimal behavior of the household over time, we nevertheless have to let the household interact with the firms to substitute out for these endogenous variables, such that in the end we get the system of two differential equations just in terms of exogenous parameter values and the two endogenous variables. Now we have again the problem formulation of the utility maximization problem of households, where households want to maximize the discounted stream of lifetime utility by choosing the consumption path optimally from time 0 up to time infinity. The instantaneous utility function multiplied with the effective discount factor, which is now e to the power of the population growth rate minus the rate of depreciation. And as we said before, n is in absolute terms smaller than rho, and that means that the exponent here is negative, and indeed the future utility is weighed down. Now, households maximize this subject to the flow budget constraint. That's the accumulation of assets as we had it on the previous slide. That takes into account income minus consumption. So these are savings of one person here. And if the population grows faster or the size of the household grows faster, then the net effect is that we have to save more in order to bring everybody in the household at the same capital level, so we have a certain dilution of assets or capital later on when capital will be the only form of asset available. Initial assets are given, and we have the endpoint constraint, the transversality condition, that is the same as before except for the fact that population growth now shows up in the discount factor. The future developments of the wage rate and the interest rate are again known to the household, so we again have perfect foresight. Now we again solve this by means of the present value Hamiltonian. So we set up the present value Hamiltonian, the utility function times the discount factor here, plus the co-state variable multiplied by the right-hand side of the constraint, the dynamic evolution. And here we just summarize the effects of A here. So we see here we have plus R times A minus N times A. So if we put it together, we have plus R minus N times A. Now the necessary first order conditions for an interior optimum are, as before, the derivative of the Hamiltonian with respect to the choice of consumption, which is the derivative of the instantaneous utility function with respect to consumption multiplied by the discount factor unchanged because it doesn't contain consumption. And we have the consumption level showing up here as well, so we have minus lambda has to be equal to 0. Again, that's the optimality condition. And we cannot increase our lifetime utility anymore by changing consumption if it is fulfilled. The second first order condition again provides us with the dynamic constraint. It's the derivative of the Hamiltonian with respect to the co-state variable that has to be equal to the derivative of assets. And that means we have this expression, this expression is equal to the evolution of assets, and we get equation number 2. And the third first order condition is the derivative of the Hamiltonian with respect to assets, and that has to be equal to the negative of the derivative of the co-state variable. Now if we take the derivative with respect to assets, we see assets do not show up in the first term, assets only show up in this term, so the derivative is lambda times R minus N. So this derivative here has to be equal to minus lambda dot, and we can reformulate this, we bring lambda to the other side here, then we have the negative of the growth rate of the co-state variable would be equal to the interest rate minus the population growth rate. And again we have the transversality condition that states that the net present value of assets has to be equal to 0. On this slide we have again the summary of the interpretations of the three first order conditions, where the first one, as I said before, is an optimality condition, that overall the value of the Hamiltonian overall utility could not be increased by changing consumption. So that means that the positive utility of more consumption today and the negative utility that is induced by the associated decrease in future consumption that is due to the fact that I would run down assets by consuming more today, these two effects balance each other off if this first order condition is fulfilled. The second first order condition provides us with the dynamic constraint, the flow budget constraint that has to hold along the optimal path. And the third first order condition is that the rate of decrease in the shadow value of the state variable, which is the level of assets in this case, has to be equal to the effective discount rate. Now, why is this the case? If the shadow value decreases more slowly, that means that I could increase my lifetime utility by raising the saving rate. So if I save more, then assets would accumulate faster, and the shadow value would therefore decrease at a faster rate. And as long as the shadow value decreases more slowly than the effective discount rate, saving more would increase my lifetime utility. On the other hand, if the shadow value decreases faster than the effective discount rate, I could reduce my saving rate and increase my lifetime utility, because in this case I save too much in a certain sense, and so decreasing the saving rate would then be lead to an increase in overall lifetime utility. Now, only for the saving rate at which the growth, the decrease in the co-state variable, so in the shadow value of assets, is the same as the effective discount rate, I cannot increase my lifetime utility by reallocating assets over time. Again, as in the example that we had when we talked about dynamic optimization in continuous time, we have a system now in two dynamic equations, in the co-state variable and in the state variable, so in lambda and in A. However, for economic interpretation, we would rather want to have a system of equations in the control state space, with the control variable being consumption. So we want to get rid of the co-state variable lambda and instead have a dynamic equation in the control variable consumption. So we follow the same steps as before to get such a system of equations. And the first step is to take the logarithm of the first order condition, so of this equation here. And now we already know we get the logarithm of the derivative of the utility function with respect to c plus n minus rho times t multiplied with the logarithm of e, and that's 1 here. And we brought lambda to the right hand side before, otherwise we could not take the logarithm as easily. And we have on the right hand side the logarithm of lambda. If we differentiate this expression with respect to time, we again get the growth rate of the co-state variable, and we get here the derivative of the logarithm of u prime of c, so that's 1 over what we have in the logarithm, u prime, times the derivative of the utility function with respect to time, which we will see again. We have to apply the chain rule for that. We have to take the derivative of the utility function, of the first derivative of the utility function, which is the second derivative of the utility function, and we have to take the derivative of consumption itself with respect to time. So we get this expression then. Taking the derivative of this term with respect to time yields n minus rho. So that's clear. And then we can plug in this expression that we've derived here. In this expression we can plug in the expression that we have from the third first order condition for the growth rate of this co-state variable. So here we've derived the negative of the growth rate of the co-state variable. If we bring the minus sign to the right hand side, we have n minus r, and that's what we plug in on the left hand side. And now there is only one difference to the situation we had in the chapter on dynamic optimization, and that is that the population growth rate shows up here, where we have population growth or growth of the representative household, while in the dynamic optimization part we did not have population growth, so n was 0. However, we see here, if we plug in n minus r on the left hand side of this equation, and we have n also on the right hand side of this equation, then n drops out again, and in the end we again get our consumption Euler equation with the same form as we had it previously in the chapter on dynamic optimization, where we know, and we'll see in a second, that the term in the denominator is again the coefficient of the utility function if we use an isoelastic expression for the utility function. Now this is exactly what we have on the next slide. We have the isoelastic utility function here, and if we compute consumption times the second derivative of the utility function with respect to consumption, divided by the first derivative of the utility function with respect to consumption, and take the minus side of that, then we get theta. If we plug it in, we have the consumption Euler equation as before. So the higher theta is, the more people want to smooth consumption, so the less likely they are willing to take the risk of ending up with a low level of consumption in one period in exchange for a higher interest payment. And again, the inverse 1 over theta is the elasticity of intertemporal substitution. Plugging that in the consumption Euler equation from before, we again get the growth rate of consumption as a function of the difference between the interest rate and the time preference rate, rho, measuring impatience, divided by theta. And the interpretation is as before. So if the interest rate is high in comparison to individual impatience, the financial markets overcompensate households for their impatience. So households would get more back in terms of capital income than what they would want to have as an exchange for their impatience. So in this case, R minus rho would be positive and they would save. And saving is consuming less today and more in the future. So consumption growth would be higher. The converse holds true if the interest rate is smaller than the time preference rate. In this case, the numerator is negative, and we have negative consumption, consumption growth. So consumption is decreasing, meaning that people consume a lot today, but they run down their assets and therefore can consume less in the future. So we have this saving if this consumption growth path is negative. And only if the interest rate is equal to the rate of time preference, then we have a smooth consumption path over time. So impatience and the compensation for impatience exactly cancel each other off, and theta mediates the process again. So for higher theta, the difference in R and rho has to be higher. That induces a certain change in the household's consumption path. Now we can put things together, the two dynamic equations, and that's the solution of the system in the control state space. We have the consumption Euler equation here, where we bring consumption from consumption growth, the denominator, to the right hand side. So we have this expression here, and we have a dynamic equation for assets. Again, we have here income consisting of wage income and capital income minus consumption, that's savings, and here we have the capital dilution part. Now, in contrast to the example that we had when we talked about dynamic optimization, the interest rate and the wage rate are now endogenous variables that are determined at the general equilibrium by the interaction between optimal behavior of households and optimal behavior of firms. So to solve the model for its general equilibrium, we have to substitute out these still endogenous variables such that in the end we only have a system in two equations and two unknowns, namely consumption and assets, that we can then in principle solve for the general solution of the system of differential equations and the particular solution of the system of differential equations that holds under a certain initial condition and under an endpoint condition, which will be the transversality condition again. Next, we endogenize the wage rate and the interest rate, and we do this by assuming a production function of firms that is neoclassical and that is similar to the one that you already know from the Solow model with technological progress. So here we have that output is produced with physical capital, so the machines, production halls, facilities and so on, and labor, where we assume labor augmenting technological progress, so the stock of technology multiplies with the production factor labor in the production function. So as technology progresses, the production factor labor becomes more productive. And this form of technological progress allows for the solution of a balanced growth path along which all variables like capital per capita and output per capita grow at the same rate, which basically is very consistent with the figure for German GDP growth and United States GDP growth that we've seen in the introduction. There are two other types of assumptions on technological progress, one in which technology multiplies with the production factor capital, and one where it multiplies with the whole production function. But in these cases, we cannot as easily compute a balanced growth path, since they are not that prominent in the literature. Now, firms maximize their profits, and given that final output is used as the numeraire, so its price is equal to 1, we have that revenues of firms are equal to the production function, and we would have the price here, but this is 1, so this is the revenue of firms. Now we subtract outlays for labor, which is the wage rate multiplied by employment of the firm, and the outlays for capital, which is the capital rental rate multiplied by capital employed by the firm. And the capital rental rate itself consists of the interest rate plus the rate of depreciation. Now the necessary first order conditions for an interior profit maximum are that the profit function, the derivative of the profit function with respect to employment of the production factor capital has to be equal to 0, and from this it follows that the derivative of the production function with respect to capital has to be equal to the capital rental rate. Similarly, if we take the derivative of the profit function with respect to labor, this has to be 0 as a condition for an optimum, for a profit maximum, and from this it follows that the derivative of the production function with respect to the production factor labor has to be equal to the wage rate. So that implies that firms employ the corresponding production factor up to the point at which it earns its cost. And up to that point, the firm would increase profits by hiring more of the production factor. The reason is that the production function is concave. So as long as the marginal value product of capital is higher than the capital rental rate, or the marginal value product of labor is higher than the wage rate, employing more capital and more labor would raise profits. And at the point where it is equal to the cost, it would not raise the profits anymore. So firms employ the production factors up to that point, and if we have free entry, then in equilibrium these relationships would hold. So the capital rental rate is equal to the marginal value product of the production factor capital, and the wage rate is equal to the marginal value product of the production factor labor. So that's what we have from the profit maximization problem. To derive the long-run equilibrium and to analyze it graphically, we define all the variables in terms of effective labor. And effective labor is L head, defined as technology multiplied by labor. So then we have capital per unit of effective labor as aggregate capital divided by A times L, and output per unit of effective labor as aggregate output divided by A times L. And the reason for this normalization is that in the long run equilibrium, we would have that capital per unit of effective labor and output per unit of effective labor are constant. So if we analyze the system in the long run, we can draw a phase diagram with a stationary equilibrium. Hadn't we divided by A, we would have that the equilibrium would not be constant, so we would have equilibrium growth. And if we analyze this graphically, we would have to draw a new diagram at each instant. Now we can also transform the production function in terms of effective labor. We have aggregate output, which is this, divided by AL, and the production function here. And if the production function is constant, returns to scale, which it usually is in economic applications, for example, the Cobb-Douglas production function, then we can divide the first term by AL and the second term by AL. And the first term, here we get again this expression here, so capital per unit of effective labor, and the second term is effective labor itself divided by effective labor is 1, and we get, we define this expression then, the lowercase f, as the production function in intensive form. Now from this we can derive the factor prices as we had them on the previous slide, where the interest rate is the derivative of the production function with respect to the production factor capital minus the rate of depreciation. And this is the same as if I take the derivative of the production function in intensive form multiplied by A times L with respect to capital from this definition here. And then we subtract the depreciation rate. And now we see that this is the same as the derivative of the production function in intensive form with respect to K hat, because we have to apply the chain rule here. So if we take the derivative with respect to capital, we have to take the derivative of f of K hat first, and then we get the inner derivative, which by the definition of K hat would be 1 over AL. Since we have AL also outside here, the AL in the numerator and in the denominator cancel out, and what remains here is the derivative of the intensive form production function with respect to capital per unit of effective labor and the depreciation rate. So the interest rate is the derivative of the production function with respect in intensive form with respect to capital per unit of effective labor minus the rate of depreciation. And analogously, we can derive the wage rate in the economy, which is the derivative of the production function with respect to labor, as we've seen it on the previous slide. And that's the same as the derivative of the production function in intensive form multiplied by A times L from this definition again, with respect to the production factor labor. Now here we have to apply the chain rule, then the quotient rule, and here the product rule again. So what we get is the derivative of the production function in intensive form, because we take the derivative of k over AL with respect to L here. So what remains then is the numerator, the derivative with respect to L, which is 0, minus the numerator unchanged, k, times the denominator, the derivative with respect to L, which is A. So we have here from the chain rule and the quotient rule this expression multiplied, then we have to apply the product rule by AL. And then from the quotient rule we have AL to the power of 2 in the denominator. And here from the product rule we have to also take the first term unchanged multiplied by the derivative of the second term with respect to L, and that's the production function in intensive form multiplied by A. So we had to apply several rules for taking the derivative, but we can simplify here. So if we divide by AL squared, then a lot drops out here. So we have here A, we have here A, so A drops out, 1L drops out, and what remains here is minus uppercase K divided by 1L. And then we can transform this again. If we multiply the whole expression by A and divide by A, then we can take instead capital per unit of effective labor here. And the whole expression then, since we multiplied the numerator by A here and we have an A here, we can put A in front of the whole expression. And what remains in the end is f of k hat from here minus f prime of k hat. And we said 1k hat remains here. So the expression that we get for the wage rate is then technology multiplied by the intensive form production function minus the derivative of the intensive form production function times the capital stock per unit of effective labor. So these are the two expressions for the interest rate and the wage rate in the model. Now we use these two expressions for the wage rate and for the capital rental rate in the dynamic evolution of assets, or the capital stock as we will see in a second, and in the consumption Euler equation to get rid of the endogenous variables of the wage rate and the interest rate. And we also assume that there is only one type of saving vehicle, only one type of asset, and that's capital. So then we can rewrite the asset accumulation equation in terms of capital. So then we just substituted A by K. Then we plug in the factor prices. So we plug in for the wage rate A times the production function in intensive form minus the derivative of the production function in intensive form multiplied by capital per unit of effective labor. That's the wage rate as we've seen before. So now it's plugged in here. Here we plug in the interest rate. The interest rate is the derivative of the production function in intensive form with respect to capital per unit of effective labor minus the rate of depreciation multiplied by capital per worker here still, minus consumption per worker, and minus the dilution term per worker. Now what we see here is that in this equation we have two types of variables. So we have variables defined in terms of efficiency units of labor, and we have variables that are still defined in per capita terms. So in the end we want to transform this equation such that it is solely determined by variables defined in terms of efficiency units of labor. Now how do we do that? First of all, we reformulate the capital accumulation equation in growth rates. So we divide it by K, and we get the evolution of capital per worker, and on the right hand side all the terms are also divided by K, such that here this K drops out, Here the k drops out and we get this expression. Now we see that actually lowercase k is in the denominator and a is in the numerator. But this is nothing else than the inverse of k hat. So a over lowercase k is the same as 1 over lowercase k hat. So we can write this term here as the first term divided by k hat minus the second term divided by k hat, and here the k hat then drops out. Then we have another f prime of k hat here, and here we have an f prime of k hat, and we see one is negative, one is positive, so in the next step these two will cancel each other off. Here a minus delta remains, and here we didn't change anything yet, so we have minus c over k and minus n. So that means these two terms drop out. Here the first term is just in terms of efficiency units of capital. And now here we still have consumption per worker and capital per worker in the denominator. But this is very easy to transform this expression in terms of efficiency units of labor, because in order to do so we would have to have the numerator divided by a and the denominator divided by a. So a actually drops out, so that is the same as c hat over k hat. And then on the right hand side we got rid of all the variables that involve per capita terms, and we only have variables in terms of efficiency units of labor. And here we used these definitions where I said here that capital consumption per unit of effective labor divided by capital unit per unit of effective labor is just defined as c over a times divided by k over a, and that's the same as c over k. So that this term here and this term here, they are the same. Now what we still have to do is to transform the left hand side in terms of variables measured in units of effective labor. To get this, we note that capital per unit of effective labor is defined as aggregate capital divided by A times L, which is nothing else than capital per worker divided by A. Now we can derive the growth rate of capital per unit of effective labor by taking the logarithm of this expression and then taking the derivative with respect to time. So that was the rule of calculating growth rates in continuous time, as you remember it from the chapter on dynamics, basically. Now, if we take the logarithm, we get lowercase k minus a, minus the logarithm of a, and if we take the derivative with respect to time, then we get the growth rate of capital per worker minus the growth rate of technology. And the growth rate of technology we denote by G. And that implies that the growth rate of capital per unit of effective labor is equal to the growth rate of capital per worker minus the growth rate of technology, so minus G. And now we can plug into this expression the expression that we have above for capital per worker. So we plug this expression in here, and then we get an equation, as we will see on the next slide, where the variables in terms of units measured per worker do not show up anymore. All that shows up are variables measured in units of effective labor. So after we plug this in, we get the next expression here. We have the growth rate of capital per unit of effective labor on the left hand side, and we have the expressions from before, and the n minus delta here, and minus g comes in from this expression here. And then we can just reformulate, so we multiply by k hat. So then the first term here, we don't have k hat in the denominator anymore. In the second term we also don't have k hat in the denominator anymore. But here we have to multiply n minus g minus delta by k hat. Now that's the dynamic evolution of the capital stock per unit of effective labor at the equilibrium in the model at which firms and households interact, so where the wage rate and the capital rental rate are substituted out. And now one already recognizes the analogy to the fundamental equation of the Solow model, which looked very similar. So as you remember from the Solow model, There, the fundamental equation was that the derivative of capital per unit of effective labor with respect to time was the savings rate, which was given exogenously, times output per unit of effective labor, so the production function in intensive form, minus this term here, so n plus g plus delta times capital per unit of effective labor, which is actually capital depreciation plus capital dilution here. And now we see that there is just a difference in the between the Ramsey-Cass-Koopmans model and the Solow model, in the sense that instead of the exogenously given saving rate times f of k hat, which we had in the Solow model, we now have the production function f of k hat minus consumption per unit of effective labor. And consumption per unit of effective labor is again an endogenous variable, an endogenous choice variable of the household, so it's determined endogenously in the model. And with that, basically, what is determined endogenously in the whole expression is the saving rate. So households in the Ramsey-Cass-Koopmans model choose the saving rate endogenously, and in the Solow model, they take the saving rate as an exogenous parameter, basically. And now we can apply a similar transformation to the consumption Euler equation, or the Keynes-Ramsey rule, as this is also known in the Ramsey-Cass-Koopmans model. Now, we again know that consumption per unit of effective labor was defined as aggregate consumption divided by A times L, which is consumption per capita, or per worker, divided by technology. Again, we take the logarithm and the derivative of the result with respect to time. So taking the logarithm of this expression leads the logarithm of consumption per worker minus the logarithm of technology. And if we take the time derivative due to our rule of calculations for growth rates, we get the growth rate of consumption per capita or per worker minus the growth rate of technology on the right hand side. So the growth rate of consumption per unit of effective labor is the growth rate of consumption per capita minus the growth rate of technology, so technological progress. And now we can plug in here the consumption Euler equation that we've derived above in the utility maximization problem, so in dynamic optimization, and that's again the interest rate minus the rate of time preference divided by the coefficient of the utility function that is an indicator of risk aversion of households, or of the inverse is an indicator of the elasticity of intertemporal substitution. Now if we plug that in, we get the growth rate of consumption per unit of effective labor, which is the same as the growth rate of consumption minus the rate of technological progress, as we see here. And we see the interest rate is still endogenous here, but then we can just substitute it out by the derivative of the production function in intensive form with respect to the capital stock per unit of effective labor minus the rate of depreciation, and then we have only parameters or endogenous variables that also show up on the left hand side of the system of equations on the right hand side. Then we have two dynamic equations in two unknowns in the control state space, consumption per unit of effective labor and capital per unit of effective labor. Now, to solve this dynamic system for the particular solution, we would need two additional conditions: an initial condition for the initial capital stock per unit of effective labor and an endpoint condition, which is the transversality condition again. Now, I don't use too many words on that here, but as is intuitively clear, the transversality condition would again be the limit as time goes to infinity of the capital stock per unit of effective labor multiplied by the growth factor of capital per unit of effective labor needs to be equal to 0. Now the growth factor of capital per unit of effective labor is then not only the interest rate itself, but the effective interest rate. So we take the population growth rate minus the average interest rate over time. And since the growth rates of capital and capital per unit of effective labor differ by the growth rate of technology, also the growth rate of technology shows up here in the exponent times t. So this expression has to be equal to 0, which then rules out Ponzi schemes in which individuals would indebt themselves indefinitely and pay back their previous debt by incurring ever a higher debt. And the interest rate is again the average interest rate over the remaining lifetime horizon. Now if we plug in for the interest rate the expression that we've derived before, f prime of k hat minus delta, we take the integral over time from this expression here and we have the minus sign outside, then we get this expression for the transversality condition. Now we summarize the solution for the Ramsey-Cass-Koopmans model. The model is described by the two differential equations, the Euler equation or the Keynes-Ramsey rule for the evolution of consumption per unit of effective labor, so that's the control variable, and the capital accumulation equation in terms of effective labor, which is the state equation. We have an initial condition on the initial capital stock. While the initial condition on consumption is unknown, that's a choice variable, but we have an endpoint condition for capital, so we can solve, in theory, this system of differential equations for the particular solution.